It's my pleasure to welcome everybody to the second day of the first Unither conference on nanotechnology, nanomedicine, and telemedicine. And today we'll be spending the first half of the day on nanomedicine and the second half of the day on telemedicine. My co-chair will be the chair of today's sessions, Dr. Barry Blumberg, and Baruch has about 10 or so minutes of introductory observations for all of us, and thereafter he will introduce the first speaker and moderate the first panel, and we'll take it from there. So generally the same format as yesterday, and thank all of you for not being scared away by anything yesterday and coming back again today. Baruch?
Thank you, and bon matin to all. Would like to make a few remarks. Much of it based on the talks that I heard yesterday, and try to. You can shut that off now, please. Much of it based on what I heard yesterday, and coming at it from a biological perspective, which has been influenced by the fact that I worked for NASA for some years, and NASA is primarily an engineering organization. 85% of the professionals are engineers, only 15% or so are scientists. So there is always something of a conflict between the need to get a machine up in space and the desire to do research. Now, the model for robotics is roughly speaking a live model, or a human model, actually. But there are differences in the engineering approach and the biological approach. So one of the big features of biology is variation. No two people in the world are the same. And when we start thinking about having swarms of robots or swarms of nanobots or of nanoparticles, the general thought is that they would all be pretty much the same. But there is the possibility of building variation into it, which raises the interesting notion that you could have kind of evolution of replicating robots as a consequence of the presence of variation and the exposure to different environments. The cells, which is the unit of biology, they are under genetic influence. That is, they have a kind of a central organizing facility that can send instructions and receive, in effect, receive data. But the genetic control is not in a strictly hierarchical fashion, and it's not a military-style command and control type of relation between the blueprint, you might say, that's determined, the blueprint that's given by the genome, because there are many influences on the effects of the gene. For example, there are post-translational effects, that is, after the protein's produced. A lot of things happen. One of the most important being the insertion of glycoproteins onto the surface of the genes. So you can have identical protein base, but different glycoproteins. And that variation really makes a big difference in the function and the location, the place, the tropism, you might say, of the protein. So even though you have identical basic proteins produced by the gene, the final product, the thing where the rubber hits the road, so to speak, may have a great deal of variation due to glycoprotein connections, and also others, methylation and other features, phosphorylation. So the genetic information isn't directly connected to the genes. Furthermore, there are always paragenetic phenomenon, influences within the environment of the cell and influences outside the cell that have an impact on the function and the way that the post-translational protein operates within the body. So the question is, can you build in some of these aspects, or would you want to build some of these aspects into a robotic device, which ordinarily has a kind of, usually has a kind of single purpose, pumping a drug into the blood. But then if we think, beyond that to much more complex and nuanced robots, we begin to examine the kind of variation that occurs in biology. Now, another feature of cells is differentiation, and the fact that every cell has the same menu of genes as every other cell, and but they differentiate to special purposes. The cells that go to the liver, subserve liver functions, the ones that go to the kidney, to the gut, to blood system, and so forth, the immune system, many of the genes are turned off, and the ones that are required for that particular function are turned on, but the genes are still there. Well, then the concept of de-differentiation, that is, you have differentiated cells, and then they go back to their de-differentiated form, and then you can re-differentiate them. That is, you can take a cell and have it do totally different functions by this process. Dolly, by the way, was the example of de-differentiation and then making a whole animal out of it. That's in many ways why it was such a sensational piece of research. So you can begin, let's say you wanted to have a pretty complex robot subserve multiple functions. So it lands on Mars or something, and then it has a mobility function, and then you want it to transmit information, so you de-differentiate and you sort of pull out the communication capabilities and so forth. It sounds like science fiction, but that's what the human cell is capable of doing. Now, the other thing is that I mentioned this yesterday. The human genome carries with it its memory of the past. And we share it with our many homologies as you go back to more simpler forms of life. As I said, we share about a third of our genes with archaea, one of the very simple, one of the earliest forms of life as far as one can tell. And that means that the cell isn't designed for perfection, because it retains much of this past memory that had an important function in the past, on the possibility, you may even say probability, that those functions will be useful in the future. But it also retains within the same gene the functions that serve the archaea. And that's, in engineering terms, is not totally efficient. Because in engineering, we look for a highly efficient economic use of the energy that's expended and the controls to which, the commands to which it will respond. On the other hand, you may not want that in a robot. You may want to follow an engineering model rather than a sort of strict biological model, and that's in fact what happens. And then there's, again, this, I think, a very fascinating phenomenon of the way that cells communicate with each other. One of the really striking examples is this quorum sensing that I mentioned briefly, I think, during one of the discussions, where you have a bunch of bacteria that form these biofilms or biomats, and they communicate with each other. And it's one of the ways they resist antibiotics. It's not just the protective coat that's established by the biofilm, but some kind of sense of coordinated activity that allows them to work together. These would, again, be cells that are, generally speaking, somewhat different from each other. Now, just another aspect of it is something that becomes very apparent from the talks we heard yesterday, and I believe some will hear today, is that robotics and, in many ways, the kind of artificial intelligence and that we've heard about is very much of an applied science. And the project starts out with a known goal, and you want to pump a drug, as I said before, or put some contrast medium in an appropriate place, or attach to a cancer cell. So it's an objective. It's an engineering type objective. It's like going to the moon. You can see the moon, and you know that's where you want to go, and you want to devise many methods, machines, and so forth to be able to do that. Well, that's the opposite of basic research. In basic research, you don't know what the goal is. When you know what the goal is, that in a way is the end of the research. And I have a sense that the field may suffer. I don't know the extent of basic research in the field, but it's because it's so goal-directed. If you are going towards a goal and you make an observation that looks really intriguing, something you've never seen before, and you say, "Boy, I'd like to kind of look into that," but no, you have marks you have to hit each time you give a quarterly report, because you're looking towards a goal. And you can't say, well, I'm not going to worry about that next mark. I'm going to go off and investigate this thing that I never expected to see. And I don't know where it's going to lead. That's not allowable, in particularly if it's an industry-funded project where people are on time constraints. They want to get the matter done as soon as they can. So again, this is a question in a field that I really don't know very well about what kind of impetus there's given to being able to follow one's curiosity. I want to point out, I think, in my mind, the future of science in our country and in every country is to investigate these things that we don't know, because that's the way whole new ideas are come forward, and whole new industries are founded. And the tradition of Western science is to advance in that fashion, and is to discover new things with unknown applications, but with the certainty that if you make these basic investigations, it's going to lead to something valuable. You know that's going to happen. What you don't know is what it's going to be and what direction it's going to take. Then there's this question, can you, what is it about a human that makes them different than a machine? And for example, in NASA, there's always has been a debate more outside of NASA than in it on whether we should have human exploration. And I have that first image, if I can see it now, please. This is a picture of Harrison Schmitt on the moon. He and his co-astronaut were the last two people on the moon, right? That was a long time ago. And Harrison was the only, Jack Schmitt, as he's known, was the only trained scientist who went to the moon. He was trained as a geologist. And he wrote a field trip report after he got back. And if I can see the next one, please. And he makes the point there that he was able to make observations, because he was a human, that a robotic device could not have done. Now, one of the great abilities that humans have is to be able to kind of deal with stuff they've never had any experience with in the past. In other words, they can see and perceive that something is new. Now, can you expect a robot that's been programmed by someone, by another human, and programmed on the basis of known knowledge? Can you train it to perceive, understand, question, be curious about something that it's never seen or conceived of before, nor has its programmer? Well, those are some impressions I've gained. It's only half the meeting's over. I'm sure there'll be many others, but you'll be spared from hearing my comments on those. And I'd like to start the session. Martine has requested that I make sure that you all keep to time, and we slept a little bit yesterday, but to my mind it wasn't all that bad, and people got to say what they wanted to. Dr. Peter Molnar will be our next speaker. He